Okay, so we can start final session. Okay, so final session is for the network tutorial and talk for some of the tutorial. Okay, so this stuff.
Okay, so in this tutorial session, we mainly perform the two kind of handles. The first part is about the basics of the network. Sorry, first of all, all of you can read this GitHub repository, I guess. Is there any problem to visit this website? GitHub? So today, organizer will send you some email about this information. So by clicking the URL, you can visit this GitHub repository. And here we have some IPython notebook and what? Okay, okay. So anyway, here I shared some IPython notebook for the today's hands-on tutorial, and also some document about the tutorials in this slide. Also, we have the lecture slide today. Then the first part is about the basics of the tensor network. So today I introduce you what is the tensor network, and we discuss about the volume of behavior of the random vector or the area of behavior of the physical ground state. And here you can directly calculate such kind of behavior by using the Python notebook. So that corresponds to the exercise 1. So here you can perform the calculation of the entanglement entropy, which I defined in today's lecture, for the random vector or ground state of the one-dimensional models or the pixel data. And probably this exercise 1 is sufficient, but if you are interested in the other part, so you can perform the exercise 2 or exercise 3. The exercise 2 is related to the NPS approximation for given quantum state. The quantum state or the segment. So you can perform the technique I explained in the lecture. So as I explained, any quantum state can be represented as a matrix product state. And by neglecting the smaller singular values, we can approximate the quantum state in the efficient matrix product state. And here you can see the such kind of approximation in the exercise 2. And the exercise 3 is the more advanced. And so, although I didn't explain what is the DVD or IDVD, that is explained in the yesterday's lecture, I guess. But here you can perform that kind of simulation based on the NPS. Okay, so the second part is the hands-on of our open source software MS. That is the open source software for the simulation of the ground state of two-dimensional lattice model. So you can perform not the variational, kind of the variational calculation based on the infinite tensor product state. And that is the second part. So let's move on to the first part. So I try to explain how to use my Python notebook on the Google Cloud. So first, to run the exercise 1.1 that corresponds to calculate the entanglement entropy scaling of the random vector. Please upload this Python notebook to your Google Cloud, or if you just run your Jupyter notebook in your environment. Then, in my case, I use Google Cloud. Then here is a copy of this my Python notebook. So basically, here we have I use the Japanese titles or something like that. But anyway, you can learn this notebook, especially on the Google Class. And what you see is like a figure of the scaling of entanglement to be like this. So here we have two input parameters. So here we define our vector space. The parameter, sorry, I need to use this one. So the parameter m.
Can you increase font size?
Okay. So in the second cell, we have two parameters, input parameters. They define the size of our vector space. And in the next exercise, we consider the one-dimensional spin model. And m determines the local field space. So m equals 2 corresponds to s equals 1 half. And if you set m equals 3, it corresponds to s equals 1 space system, for example. Then n is just a number of the speeds, for example. And here we set the m equals 2 and n equals 16. So we try to consider the 2 to the 16th dimensional vector space. And we prepare the random vector from this line in the third step. Then the purpose, as I explained, the Schmidt, so the entanglement entropy can be calculated from the Schmidt decomposition Schmidt way. And here we transform our vector into the matrix. So this matrix is just correspond to the Mij appeared in my lecture slide. So we decompose the system into two parts, region A and region B. And here we consider the partition of our vector. This. We partition like this. Then we perform the singular variable decomposition. So because we consider that this random vector corresponding to the quantum state, we want to normalize the length of this random vector. And so here I introduce some normalization. And finally, we calculate the entanglement entropy, something like that. And this is the output, the value. So you see that for this specific realization of the random vector, we have the entanglement entropy about 5. So you can change this setup by changing the value n, and you can observe that the change of the entanglement entropy, something like that. But probably the most interesting part is the bottom part of this notebook as the appendix. So here you can vary the number parameter n. So in this example, from 4 to 20, and we try to calculate the entanglement entropy for defined n, and plot this kind of figure. So the entanglement entropy was the same. So you can probably understand how to calculate the entanglement entropy for the given vector, and you can use this notebook. Let me check. So in this case, we consider the n equal 2 and n equal 4 to 20. So let's change the parameter m to c. It corresponds to the s equal 1 spin system. Maybe 16 too large, I guess. So here we consider 14. Well, and also to draw this kind of the graph, I consider the here 2 to 12 in step 1. So this just generates the sequence of the n. Then let's run the calculation. Then calculation is done. And in this case, you obtain the entanglement that is 6. And similarly, you find this kind of diagram. The almost volume law. So, and understand why there appear the step like picture here. So, because we consider the equipartition of the system, but here we consider the also the odd numbers for the n. So for the even numbers, we have the equipartition. But for the odd numbers, there is an imbalance between the left hand side and right hand side. So we see that this type of step. But anyway, by using this outlook, you can understand how to calculate the entanglement entropy using Python. Okay, so this is just a demonstration. Then probably the interesting part is for the exercise 1, 2, that is the calculation of the similar property for the realistic spin model. Okay, then let's move on to that. By the way, if you have any questions.
So, how do you control the maximum dimension of your diagonal matrix? And your maximum dimension 2 to the power, and in this case 3 to the power n by 2. Maximum dimension of your.
Oh, here, so maximum dimension corresponds to the 3 to the 12.
Yeah. So
how to control do you mean?
You are taking 3 to the power n by 2.
Sorry.
I am saying that what is the dimension of your matrix in the maximum dimension?
In what sense maximum?
You are doing when you are doing SVD, then U is V dagger. Then I am saying that the dimension of your S matrix, the diagonal matrix.
That is
the maximum dimension is 3 to the power n by 2.
Yes. Right.
Yeah. So, but you are taking here 3 to the power n by 2 or less than that.
So we take all of the similar values. So there is no approximation.
Okay. Okay.
So this is just a property of our quantum set.
Okay.
So yeah, connection to the tensor network decomposition, because the random vector has the scale, has the volume of scaling, so we cannot use the tensor network decomposition efficiently for this thing. Then the next, let's see the physical situation. So if I open, maybe up. So by the way, I have several interesting repositories related to the tensor network. So if you are interested in the tensor network normalization group, you can see this one. And also if you are interested in the application of ITBT technique to calculate the classical system, you can visit this one. Anyway, present repository here. And next we try to start this one. And here we copy our workbook. And in this notebook, we try to do the similar calculation, but we use the realistic physical ground state of given Hamiltonian. Then there is an important notice. So here to obtain the ground state of our given Hamiltonian, we use the exact diagonalization. So we need to put some Python code corresponding to this exact diagonalization. It is also given in this repository. And so we upload this one to the Google Cloud. Firstly, probably I need to download. How can I upload? Anyway, I have this code in my desktop. So anyway, please download this Python code that supports the exact diagonalization to obtain the ground state. Then please upload the Python code to your Google Drive or your Google Drive. Then here I am connecting Google Cloud again. Then, so you can find how to use this Python code in this slide. So on the repository exercise PDF. Then here is the instruction to how to use the Python notebook in the Google Cloud. So maybe you can understand how to upload the Python code. So first, you open the exercise in our case 1, 2 in the Google Cloud. Then click here and upload. And in this case, we need to upload the ED code. So that is in where it is. Then, so now, okay. So let's this. So now we so now the calculation is going. Basically, we performed a similar calculation for this example. So by taking the system size, and we draw the scaling of the entanglement entropy. Wait. Okay. During waiting the result, I'd like to explain the input. So here we consider some three models described by this Hamiltonian. So we can input the SG interaction and also the XXYY interaction and transfer speed. And this one is the single anisotropy if the spin is larger than 1.
So,
Okay.
we can change the spin quantum number in this
Yes,
case.
yes. So the parameter and determine the spin quantum numbers. So n equal to corresponds to x equal 1/2. So n is just the range of the local Hilbert space. Okay, and so here is the parameter set for the default combination. So here we consider the x equal 1/2 spin system with a transfer speed ideal model. So because we have SG interaction and SX is finite. And then we consider the 16 spins. Then and here we use the open boundary condition. Then by perform here we obtain the ground state by using my exact diagonalization code. If you are interested, please see this ed.5. It is very simple. So just use the sideline for the sparse matrix diagonalization. Anyway, then we just perform the similar analysis. So the probably that this information is almost instructive. So here is the spectrum of our singular values. So as I explained in the lecture, the singular value spectrum almost decay exponentially. So it indicates that the entanglement, quantum entanglement in this system, quantum state is very small. And actually, for this setup, here is okay. The value of the entanglement entropy itself is 0.6. If you remember the value in the case of the lambda vector, it is around 6 or 5 or something like that, and it is one magnitude smaller. And yeah, we draw the similar curve by changing the system size. So again, here we fix the parameter for our quantum model, and we just change the system size, and we calculate the entanglement entropy and draw the design of the curve. Okay. So here, let's change the parameter. So for example, we can simulate the transfer speed ideal model with very weak transfer speed. So previously I used H is equal to 0.4. It is somehow in the vicinity of the quantum critical point, but here we choose the very small transfer speed. Then let's run this notebook. So in this case, you see the entanglement entropy is almost same with the previous one, but slightly smaller, I guess. But if you look at the decay of the entanglement entropy, so you see that the number of let's say finite, in somehow finite singular values are very small compared with the previous parameter. And if you see the size dependence of the entanglement entropy, you may realize the difference, but this way. Okay, something like that. So what happened? Why 14 is so special? Probably, I guess the transfer speed is too small, and there appears many singular values close to the very close to 0, and it causes some error. I'm sorry. So let's change the parameter. Let's try over here. let's see. Maybe. Anyway, we have calculated. Probably we need to reset the with the problem here, initial direction is maybe we need to restart our post.
All right, can I have a question?
Okay.
So, absolutely, you will ask me.
Okay. So you try to run this ED. Yeah. So what one? Okay. So this is using the Google Path. So so in this tutorial we use this ED file as the somehow the library. I'm sorry. So please. So in order to run this ED, we need to input some parameter from the command line. So it is not supposed to be this Google parameter.
So the ED Python code is used in
So exercise 2, we
import, I think, ED Python.
yes. So just upload this ED file in directory. So the how to upload is explained in the exercise of PDF. Anyway, what we obtained is something like that. So this is the expected result. So if the transfer speed is so small, we see the almost flat entanglement entropy. So please see the range of the batch analysis. It is almost flat. Okay. So if the parameter our quantum state is far from the quantum critical point, then we can easily observe the one-dimensional error. But in the previous example, we changed the parameter transfer field as 0.4, and actually the critical point is 0.5, and so 0.4 is very close to, somehow very close to the critical point, and so we observe the sum and events.
Why is it falling? Why is it like 20?
This is kind of the numerical error or something like that. So here, please see that here is 0.678 and this is 0.698.
Okay.
So minus I think or something like that.
Yeah, let's see the y-axis.
Is so for higher gamma well higher x
Sorry.
is so for higher h.
I
It is a rule like taking one.
yeah. Yes. So if the the disorder phase of the So let's find the higher transfer speed, and globally one is sufficiently large, I guess. Then based on this singular value spectrum, I guess we observe somehow independent entanglement. Let's see. We need to increase the transfer scale value much more. But actually, we observe the saturation of the entanglement entropy to the area rho at the length scale corresponding to the correlation matrix of the your quantum state, basically. So as you know, in the vicinity of the quantum critical point, the correlation length diverges. So it is very difficult to observe the saturation of the entanglement entropy. Okay, it's nice. So like this. So we observe the flux behavior or the permanent, permanent or random case. Okay. So finally, so you can enjoy by changing this kind of analysis by changing the parameter by this notebook. So you can probably consider the high level model. So by considering by set the JXY, or you can also consider the difference in quantum number by setting, for example, m equals 3, it corresponds to S equals 1 quantum spin system, and you can also, if you are familiar with the quantum spin system, you can analyze the case of the how they act or something like that. And
so this value is very less, right? 0.08 something.
sorry.
So this value is 0.08 around, so it is very less. I think.
Sorry, this is the value corresponds to the H equals 1.
Yes.
And in this case, we obtain this one. And what is your question?
So my question is, it's less. I mean, so in the ordered state, it was around 0.693. So long to kind of that value.
So you mean the value of the entanglement entropy. So if in the limit of the infinity large H, and it should be zero.
So it's zero because it's completely random.
Or
These
just a product. So yeah, you can enjoy this example by changing the parameter, or if you are interested in the different application, you can the similar analysis for the share images. So let's upload. In this case, we need the images to represent to calculate the outset entanglement entropy. So here I use this one. So I need to copy this one. Use my I want to copy and so here we perform the similar analysis for the data from the image. So this is similar, but to create the how to say data correspond to the quantum state, we train our pictures for the given n or n, and in this case here, then this is the string image like this. So let's try this example. So in this case, we observe that the scaling with entanglement entropy as like this. So in this picture image, you realize that the value of the entanglement entropy is small compared with the random vector. However, we see some type dependence. So unfortunately, here I use only one picture image, and so we cannot say not so much important information about this specific picture, but you can analyze the data set of your pictures or data set distributed by some company or something like that. You can analyze the property of the entanglement entropy of the data set, picture images or something. So actually, this entanglement entropy is related to this spectrum of the singular value decomposition of the pictures. Then, yeah, you can, if you try the different pictures, you will see the different behavior of the singular value spectrum, and I guess it does same. Okay. Anyway, and this is the explanation about the exercises on the first part. So here I only showed you the exercise one, but we can perform the similar analysis and do this. So we try to approximate the previous vectors by the matrix product state. And as I explained in the main lecture, so if the entanglement entropy is not so large, or it is satisfied the area of the one-dimensional area is satisfied, we can efficiently approximate our vector and the matrix product state. And you can check such kind of behavior by performing the exercises. And also, we can try to approximate our ground state of or given Hamiltonian by using the imaginary time evolution technique. And so the point is that in the exercise 1 and exercise 2, we use the exact quantum state and exact ground state, and we check that there is the area rule. And so it indicates that if you perform the exercise 3, the small order dimension is sufficient to simulate or approximate the such ground state. So if you are interested, please try this example. But today, I don't have so much time. So I'd like to move on to the second part. So, but if you have any questions, okay.
So in this problem, you are always putting at the half of the cone to find the entanglement entropy for the singular value. So it may happen they are locally more entangled, suppose singularity.
Yeah, you're right.
So that may change the problem because they are locally they're more entangled, but they're not more entangled at the middle. May that happen or?
So here we just calculate the entanglement entropy for the specific division partition.
Yeah.
But as we said, that the entanglement entropy can depend on how we divide the system into two parts, for example. And so here for the real problem, we need to check this kind of the property. But we believe that the physical system, the state can should satisfy the area of the entanglement entropy, and we believe that we can approximate the quantum state efficiently by for example matrix product state. So yeah, actual entanglement entropy entanglement distance depends on the position or something like that.
Thank you.
Thank you. So any other questions? So please enjoy this exercise later. Then the second part is the hands-on tutorial of our open source software tennis. So unfortunately, it is written in the C++, and so it is not so easy to run it on your laptop. But as I send you some information, if you prepare your virtual environment using this material slide, you can try this tutorial. So here I show you the tutorial based on this slide. So here I demonstrate you how to use this open source software. So if you have prepared your virtual environment, so you can perform this hands-on with okay. Let me explain. Okay, so this is the explanation of the open source software tennis. It is developed by myself and the collaborators. And basically, this tennis can calculate the ground state of the two-dimensional quantum models, especially for the quantum spins and also the Bose-Hubbard model. And the property is like this. So far, we only support the optimization based on the imaginary time evolution. As I explained in the main lecture, the imaginary time evolution sometimes trapped in the local minimum. So you should use the variation optimization nowadays, but so far in this application, we don't support the variation optimization. So we can use only the imaginary time evolution. The second property is this one. So this code is massively parallelized using the NPM and OpenMP, hybrid parallelized. So we can use this software in the supercomputer. The purpose of this open source software is to prepare the environment for using the tensor product state calculation. So easy calculation for the quantum spin of bosons or easy access to the standard two-dimensional matrix. We don't. The purpose is to perform not perform the very accurate calculation by using the two-dimensional tensor network state. So our main purpose is to prepare the easy environment to use the tensor network. So yeah, okay. But for example, you can easily calculate the magnetization plateau appearing in the Haber-Peralta model by using the D-10 tensor product state for the infinite size system. And if you use the 72 nodes in the supercomputer by using the 4 hours, you obtain the this kind of structure. Okay. Then this is the explanation of the features of this tennis. As I explained, we can calculate the ground state of the various two-dimensional quantum spin models and also both Hubbard models. Unfortunately, so far we don't support the fermions, so we can deal with the both features. And in this test, we represent the quantum state using the square steps. Oh, sorry, Jenka product state. And the models on other 2D lattices are mapped onto the square lattice. And to contract the infinite tensor product state, we need some approximate procedure. And in this test, we use the Common transfer matrix. It is the same as I explained in this lecture. Okay. Then, yeah, we support the hybrid parallelization. So basically the tennis can, in principle, tennis can treat any kind of the two-dimensional models, but we support some predefined models and predefined lattices. And here is some kind of the predefined model. So we can treat the general spin S models with this kind of interaction. So X, Y, Z type interaction and how to say by quadratic interaction and field current field and also the single answer field. So what you need is to just input these parameters to simulate the ground state of these models on any lattices. Sorry, not any lattices, predefined lattices. Okay. And also you can simulate the similar system for the Hubbard model. Yes. And as I mentioned, this is just a predefined model, but by manipulating the input file, you can also create different models. So different interactions or something like in principle. And this is the list of the predefined lattices. So we can treat the square lattice or honeycomb lattice or kagome lattice or triangle lattice. But you can design the lattice by editing the input file somehow. And so basically you can calculate any kind of two-dimensional lattice models if you want. Then this is the basic structure of the tennis. So we have three tools and three inputs. First, basically if you want to simulate the predefined models, what you need is to just prepare this simple formula, simply for this tennis thing. So using this input, this script, Python script, and it's simple to make the Hamiltonian and lattice information from the input for the previous model. And then the output is this standard common. This is the new input for this second part. This second part takes the imaginary time evolution operator using the total decomposition for a given Hamiltonian. Okay. And so you can directly edit this input if you want to simulate like models not defined in our tennis. And finally, the main program tennis performs the calculation of the ground state based on this imaginary time evolution operator, and also calculate the expectation value of it. So it means that also we can input the tensor product state itself into the tennis. So it means that if you have some quantum state represented by tensor product state, you can use this tennis to calculate just the expectation value. Something like that. Okay. Then, as I distributed the information in email. In this tutorial, we use the material apps, right? That is Linux virtual environment for this tutorial app. So virtual environment, and it is contains a lot of open source software related to the material science. And you can use the VirtualBox or Docker or something. And in this virtual environment, our tenant is already installed, and so we can easily use this tenant. Also, you can install this tenant in your cluster computer or your laptop or your computer. And if you are interested in installing this test, please see the document. Anyway, in this tutorial, we assume that you have this material, right? And here I'd like to demonstrate how to use this test. Okay. So because I use the Mac, first I activate the material slide like this. So in the case of the VirtualBox, we start the virtual machine on the virtual box. Anyway, in the case of the Docker, here we prepare the virtual environment. So now we can use tenant. The first, what we need to do is update the tenant in the material slide. So please type this information. So do update. So the important information is the password is right. Okay. Then next we install the tenant. Maybe it is correct. No. Yes. Okay. Anyway, it is the latest version of the test, but version is 1.3.1. Then next we copy our tutorial file from the shared directory. So copy this shared file to your, for example, directory here. And let's move to the sample directory. Okay. So please type this one. Then in this directory, we have several tutorials like the transfer speed ID model or square lattice hypermodeling type model or something like that. But today we only consider this first one for the application to the transfer speed ID. Okay, then yeah, let's go to the next page. But by the way, this tutorial file is also in the repository, and so you can read this one and you will try this tutorial after this session. Okay. Then the first example is to calculate the ground state of transfer state ID model. And as I explained, that there is a parameter determines the ID interaction and transfer speed. And by changing the transfer speed, we have the contact critical point. Okay. Then let's move on to this directory, or coherence test is the best. So first we move to this directory, sample directory, and here we have the several files. Okay. Then let's see the input file for the tendency. This one. So here we have several input parameters. Unfortunately, I don't have the sufficient time to explain all parameters. But for example, we specify our tensor is complex or real, and also that we define the imaginary time evolution steps. So for the 10 step, 1000 step in the simple update. Sorry, I didn't explain what is the simple update and the full update. This is the variant of the imaginary time evolution. But anyway, here we consider the simple update with 1000 steps. And here tau is the time step in the total decomposition. And here is the parameter for the corner transfer matrix environment. And here we use the chi is equal to 10, for example. And to optimize the corner transfer matrices, we need to perform the iterative calculation. So here we set the maximum iterative number, iteration number is 10. And this lattice section defines the setup of the tensor product state. So here we consider 2 by 2 unit cell in our tensor product state, and please remember that we consider infinite system, and here we assume that the periodicity of our tensor network. And this virtual dimension corresponds to the boundary range of our tensor network. So previous D, and finally we define the model. That's it. Then by performing by using this input file, we can calculate the ground state by the tensor product state. Okay, let's see. First, we perform the tense simple, as I explained, by this. We obtain the new input for the standard tennis standard. So let's see the file. So from the previous input file, the tennis simple create the new input file for the next step, and it contains some information about the Hamiltonian itself, and also the definition of the observable, or maybe in response is the definition of the imaginary time evolution. Anyway, it defines the imaginary time evolution operator in some. Okay, then next we perform. In this step, we didn't create the imaginary time evolution operator, but just prepare the Hamiltonian lattice. And next step, we create the imaginary time evolution operator by using this NSSTD. I did this step. Then let's see the input. So in this input file, we have the information of the imaginary time evolution operator that is here. So this is the element of the imaginary time evolution operator. Okay. Anyway, then finally we obtain the input for our simulation. That is the imaginary time evolution operator. And the imaginary time evolution operator is related to the Hamiltonian, and so we can calculate the ground state by using such imaginary time evolution operator. Then let's do this simulation. So quick. So we perform the 1,000-step imaginary time evolution with the bond dimension D and bond dimension for the Polar transfer matrix 10. Then the simulation done after this step. And finally, we obtain the output corresponding to the expectation value of the physical observer. In this case, sorry, I didn't mention what is the system. So, so here we consider this model. So the ferromagnetic interaction without transverse field. And so the ground state is just a ferromagnetically ordered state. And actually, you see that the output is like this. So the expectation value of the XG is 4.5. So classically ordered state. And here this is the energy. So this it corresponds to 0.5 because we consider two-dimensional square lattice. The energy per site is minus 0.5 for the ferromagnetically ordered state. And also we calculate the different nearest neighbors information. Then we can define any kind of the observables in your input file, but this is the default.
Sorry,
Okay.
what is zero mean?
Zero.
Yeah,
Okay. Here.
yeah.
Okay. So although I didn't mention the meaning of this output, generally we can calculate any kind of observable or any kind of expectation value of any kind of operator. In some cases, the operator can be complex. And here, so yes, this is the real part, and this is the imaginary part. And due to the approximation, if you use the complex tensor network, there may appear the noise in the imaginary part. But here we use the real tensor network, real value tensor network, so imaginary part is exactly equal to zero. Okay, so this is the standard calculation. So the message is like this. So we obtain the correct ferromagnetic state. Then next we turn on the imaginary transverse field. Then let's move. So I didn't mention the several output is recorded in this directory output, and so here we move this output directory to the other one. So because we calculated the imaginary transverse field equal to 0, we name this one. Then the next step is to edit our input to change the imaginary transverse field. Then I use DI to edit our input file. The place we should edit it here. So the original value is hx is equal to 0. But by changing this value to, for example, 3, we can simulate the case with the finite transverse field. Okay. Then let's see. Just redo the same thing. So first, we transform our sequence to make the Hamiltonian. And next, we make the imaginary time evolution operator. And finally, we perform the real simulation. Okay. Like this. So here we obtain the new output. The point is that, so here we have the finite transverse field, and the hx is equal to 3 is in the disordered phase. And so we have a large Sx component in the expectation value. But the point is, it is not exactly equal to 0.5. So there is some finite total fluctuation. And we have the different energies, and also we have the finite relation in the SG and SY. Yeah. Okay. Anyway, we obtain the different result by changing the parameter. Okay. Then, finally, we want to observe some kind of the phase transition behavior by using this NS. So we try to perform the similar simulation by varying the transfer. So in this tutorial, we prepared some convenient code, convenient Python script. So these two. And for this tutorial example, .py, this creates new input files for various HX transfer field values based on the simple form and run simulation. So it means that based on the parameters defined in this simple.com, we just change the value of the HX and we repeat the several simulations. And this tutorial will provide this collects relevant observables from the output, and we output the important information as a function of the transfer field. Then let's run this simulation. So first we move our output to the defined directory. Then let's run this line. So by running this code, as I mentioned, we automatically simulate the different transfer field. So it takes some time, maybe a few minutes. So yeah, automatically simulate the different transfer field. So we calculate the 16 values, different values of the transfer field. Okay. Then here we have a lot of output. So these indices correspond to the different transfer field. Then we collect the data by this script, and it gives us some output like this. Now we write this output to some file, insert it in this tutorial file. So because here we consider that the bond dimension 2 tensor network, I name the result as result D2 underscore D2. Then we just save the result to this file. Okay, so we have the result, this file. This. So next we plot our result. Then here we use this like this. So we plot the SG, expectation of the SG as a function of the transfer field, and also together with the expectation value of the SX as a function of the transfer field. And we obtain the different data. So this purple line indicates the expectation value of the SG as a function of the transfer field. And this green line corresponds to the expectation value of the SX. And here you can easily understand that if you increase the transfer field, the expectation value of the SX increases. The point is that this purple line, it characterizes the quantum critical phenomena, so the phase transition. So you can realize around here, there must be the phase transition. transition because for the larger transfer speed, the expectation value of the SD is almost equal to 0. And from here, below this point, we have the finite ST. Okay. So by using the test, you can directly calculate this kind of phase transition behavior in the two-dimensional system. So the point is that so in the case of the one-dimensional transfer speed model, we know the exact point of the critical point that is corresponding to the hx is equal to 0.5 in my definition. In the case of the two-dimensional or square lattice transfer speed model, we don't know the exact critical point. But by using this NS, we can calculate numerically the point on the critical point here. Actually, in this special case, we can perform the quantum Monte Carlo. So because there is no frustration, so the critical point is estimated around 1.5. So somehow our calculation overestimated this quantum phase transition. This is due to the small bond dimension approximation. So here we only use the tensor product state with bond dimension 2. So if you increase the bond dimension, our estimate may become more accurate. Then let's check such kind of behavior finally. So next we change again the inputs. Maybe it is better to previous data here. Then edit this input file. I guess it is too fast for you, but I'm sorry. Then the input file is here, and here this line we define the bond dimension of our tensor product state. So here is it equals to equal to. Then here we change it as 2 from 2 to 3. Then we can perform more accurate simulations. Please note that by increase the parameter D, you need a much more computation time. As I explained, asymptotically, we need a D to the 10th scale. But I guess in this smaller for the dimension D equals 2 or D equals 3, the simulation is not so difficult. Okay. Then anyway, let's perform the similar analysis. Slightly slower than the previous calculation, but you may see that D equals 3 in the output. On the laptop, D equals 4, D equals 5, D equals 6 is easy, but I guess it is not so easy to simulate the equals 7 or something. You may need the cluster computer or computer for the high performance computing or supercomputer. Okay, then the simulation was done. Then we collect the data and output the new file. So now, we did this. Right. And finally, we got the two data like this. So okay. So this first part plot the SG expectation value calculated by the answer with bond dimension 2. And the second part is the same plot with the answer of the D3. And let's see the difference. Okay. So let me find this here. So that's the result. For maybe for the larger transfer speed, we don't see any difference, and also the smaller transfer speed, we don't see any difference. But in the vicinity of the quantum critical point, we see the visible difference between the D equal 2 result and D equal 3 result. So as I explained, the known estimate of the critical point is around here. And so by increasing this bond dimension D from 2 to 3, we obtain the better result that this point is larger than 1.5. So this should be very close to 0. By increasing the bond dimension, we see that we obtain the more better than the case of the D equal 2. Okay, similarly, you can simulate the case of D equal 4, but in practice, you need to change the other parameter, like the length of the imaginary time evolution, or the parameter for calculating the approximated environment, that is the bond dimension height, to obtain the correct means that reliable result. So because here we use the imaginary time evolution to obtain the ground state. So how long we apply the imaginary time evolution is important to obtain the good ground state. And also, as I explained, we use the approximated construction of our infinite tensor network, and we need to control such accuracy of the approximation of the construction. That is controlled by the maximum iteration number of the Corner transfer matrix calculation, and also the bond dimension for the Corner transfer matrix. That is defined in, for example, here. So we need to increase here. So as I explained, typically we should take this value at least D squared. So if we simulate the case of D equal 4, this must be larger than, for example, 16, something like that. And so you may need to increase this one. This should be D squared. And you also may need to increase this iteration max that controls how to repeat our calculation to estimate the corner transfer environment. Anyway, and also this is important. So here we only perform the 1,000-step imaginary time evolution, but you may need to increase this part. And similarly, if you are interested in the quantum critical point, you also need to consider the more sophisticated imaginary time evolution that is called the full update. It's also time consuming. So here we didn't use this full update technique, but you may need to increase this value from 0. Anyway, so that is the technical tips. And basically, so this is a quick introduction to how to use this tennis. So you can find other samples in the same directories. So you can simulate the anti-thermomagnetic sphericity Heisenberg model, or you can find some sample input for the different spin quantum numbers or mechanical models. And also you can simulate the magnetization process of the square lattice Heisenberg model or triangular lattice Heisenberg. If you are familiar with the clustered spin system, you know that if you simulate, you cannot simulate the triangular lattice Heisenberg model by quantum Monte Carlo, but by using this NS, you can simulate the magnetization process of the triangular lattice Heisenberg model, and you may reproduce the famous one-third plateau of this system. And also you can simulate the hardware model. Okay, yeah. And I'd like to recommend you that this fifth part of the tutorial. Okay, so this is the final slide. So this is the defined for the tennis. So this is the repository of the GitHub repository of the NS, and you can find the manual more, how to say, it contains more information than this tutorial slide. So you can know the definition of the input file or something. And also we published some paper about this tennis. So in this paper, you can see the concept or implementation of the TensorFlow state calculation. Okay, that's it. So unfortunately, today I don't have the sufficient time to do the tutorial or all part. But anyway, if you are interested, please check this tutorial and please try this tennis by yourself. That's it. So do you have any questions? Okay.
Suppose you are calculating a ground state property of the model,
Yes.
which you don't know beforehand by any interdimensional method. So how do you check its numerical component?
Okay. So it is very important question. So because we don't know the true behavior of the unknown model, we need to check the reliability of our calculation. Basically, within the tensor network calculation, what we need is to increase the bond dimension of our tensor product state or our Corner transfer matrix environment and take the convergence. And it first you must check the convergence with respect to the bond dimension of the environment. That guarantees you that we obtain the correct expectation value for the given quantum state. Then the next step is the obtain quantum state is the two ground state one. And to check that quality of the ground state, expected ground state, we need to increase the bond dimension and check the convergence. And also we need to increase the parameter of the imaginary time evolution. So we need longer imaginary time evolution maybe or something. Anyway, we need to check the convergence by increasing the some parameters.
So in DMRG, you can consider one side or two sides. So here it is also the same method.
Sorry. What do you mean? In the case of the DMRG?
When you do calculation, you can fix one side or two sides and keep on changing the environment.
One side or what does that mean? The one side update?
Yeah, one side of DS.
So here in this specific case, we use the imaginary time equation, and we only use the case basically the two side up. But if you apply the variational optimization, today I introduced you in the main lecture, then in that case we can choose the one side update or two side update in this case. And so usually by using the two side update, we can dynamically increase the bond dimension. And so we check the sometimes the translation error or some error appearing in the bracket the bond. And it may help to check the convergence of your calculation. Thank you.
Sorry, I'm afraid saying it's time to close.
Okay.
So yeah.